So we start a discussion of Wasserstein space, that is the metric space over the given on the space of priority measures. Okay, and I know that Professor Sumik-Par already discussed some certain aspects of such a space, but we will do kind of something you already did, but also we will do some additional things regarding regularity of Mercant's displacement interpolation. And after today and next week, we will do the so-called autocalculus, which is a very important topic in optimal transport theory, okay, which will lead us to the discussion on gradient flows. Okay. So space of priority measures is a metric space. In particular, if we use the metric given by the optimal transport. So during the lecture, our X is a separable metric space. Okay. So separability means, what is separability? Dense what? Yeah, so there's a countable dense set. What? So that's what I don't know how to handle. Okay. Titles are not that important. So I just started on Wednesday afternoon, so I don't know what happened. Okay. No, okay, so let's continue. Okay, so PX, this is notation for us that it's a set of priority measures on the metric space X. So we call this a space because we will give a topology on that space, on that set. Okay, so the set with topology is called a space. Okay, and then I mean we do this by giving some natural distance. So we want to put the natural distance, but then we want the following thing. If you have, let's say, 2 points in X, little x and little y, then the distance between them should be the distance between the Dirac delta on X, at X and at Y in the space of priority measures, okay? So this distance should be the same as this distance, of course. I mean, that should be the obvious natural thing one may ask for such a distance, right? And then if you require this, that means the original space X now can be embedded in the space of priority measures by sending a point to its Dirac delta. Okay, then this embedding is isometric, namely the distance between X and Y is the same as the distance between delta X and delta Y. Okay, such a property is not seen in most other, let's say, distances on the space or priority measures or on function spaces. Because on function space, basically you, including this total aberration distance, and in function space, what you do is just you have some function, another function, you take the difference between those functions, okay, and then take norm, and then you do some integration and with some power. That's what usually you put as a distance on the function space. Is that too dark? Okay, let me not use blue color. I don't know how can I fix this? Okay, let's just do this, okay? So anyways, the point is that the usual so-called LP type distance, including at infinity or this kind of usually the distance given in the functional analysis context, they do not enjoy such property that that the embedding of x to px is isometric embedding. Okay, so why? Because, for example, if you consider x and y, okay, then if you just look at this total variance distance, then the distance between x and y, as long as x and y are different, okay, I mean the delta x and delta y, is the same regardless of the distance between x and y. X and y, the distance can be like 10 or can be million. Still, this total variation difference is 2. Okay, so regardless of the distance between x and y, so this such a distance, including all other like a functional analytic context distances, do not enjoy such isometric embedding property. Okay, this is very important feature.
What, right?
I think it's 2.
I think
Well, this is 1, right? Okay, and then this.
but is a non-negative Coulomb difference of Coulomb energy. I think if you use the
Is it 1? Okay, so I don't want to argue. So 1 or 2. The point is that it doesn't depend on the distance between x and y. Okay. All right. Okay. Then why do you require such such a distance that respect the underlying distance? Okay. So in some contexts, for example, if you consider particle dynamics, and then you may want to view, let's say, a distribution as the collection of particles, okay? And then you want to understand how this distribution changes over time, like how this distribution like satisfies some kind of PDE by looking at some OD, some dynamics of each particle following certain ODs, okay? So there, one may want to understand, treat how each particle moves, and then the distance traveled by each particle matters for, let's say, like a collective displacement of mu. So in that case, it's kind of natural to have some distance that respect this underlying, the distance of the underlying space. Okay, I think that I already told about this. Okay, so you see that this such a distance, which we already know what it is, right? The Wasserstein distance is something that can handle this requirement. Okay, so we know. So we already learned the Wasserstein distance, right? But anyways, let's just review what Wasserstein distance is. So we focus on RD in today's lecture, but of course your X can be any separable complete metric space. Okay, in particular this path space of passes is an infinite dimensional space, very large space, but you can still consider the space of priority measures over such let's say space of passes. And one of the examples of such a measure is what you know, I mean, the Wiener measure. Wiener measure is a measure that gives a Brownian motion. So for example, Wiener measure is in such space. Okay, gives Anyway, so and then there are many other priority measures on the space of passes. Then understanding those priority measures is a matter of stochastic analysis. All right. And sorry about this blue color, but this is Wasserstein distance, Wasserstein 2 distance, which is given by taking distance square between x and y, and then you integrate over possible transfer planes between mu and nu, and then you minimize. So this is just optimal transport cost, and then you take the with this squared cost. So cxy is this time here xy, and then you take the square root. Okay, that is this W2 distance, often just called the Wasserstein distance. Okay, and then there we have such property that delta x delta y has W2 distance, which is the same as distance between x and y. I mean, this property is not only for the Euclidean space, but also for any metric space. Okay. And of course, you can consider general power P instead of 2, then you can consider WP distance. All right, any questions so far? Oh, okay. That's simple. Okay. I should have tried. All right, so any question? Okay, now I mean, this W2 distance is indeed a distance, namely it satisfies triangle inequality. I mean, this is something you can prove. But maybe I suggest you to read the corresponding theorem and proof in Villani. Then you will learn about how to use the so-called disintegration of measure, okay, to prove such a thing. So your exercise, okay. But it satisfies this triangle inequality property. I mean, for any p, okay, PP. So this behaves like IP distance, but IP distance does not have such a feature that the embedding from x to Dirac delta at x is not isometric embedding in a 2D IP distance, but here you have, and this is a distance. Okay, now let us focus on just the Euclidean space as our underlying space. Okay, so then the distance xy is nothing but the difference, the norm of their difference. Okay, and I'm going to say, even, okay, so we have this RD and we have this infinite dimensional space PID, okay? And of course, X goes to delta X. So this ID is kind of a subset in the space of priority measures, okay? Just embedding of this ID into this bigger space. Okay, and then now, given any like mu and nu, we can consider the distance. Okay, and then one thing for a space to be a metric space with this distance, in this case, just W2 distance, of course, we need this triangle inequality here. And also, we need several things. First, okay, triangle inequality and symmetry. So the symmetry is obvious, right? But there are other things that WP or W2 should satisfy. What are others? Partial definition means this is equal to 0 implies mu is equal to nu, okay, as a measure. So almost every sense. Okay. Okay, maybe I shouldn't say, I mean, it's just measure set it. So it should be the same as a measure. And there's another thing, actually. What? No, metric space. What? Okay, so non-negative is obvious, right? And in fact, there's another thing. What? It is too obvious, so maybe that's why you don't catch it. Very obvious. It's like a fun piece. Of course, yes. Yes, exactly. That's important. So in the method, in the space. Okay. So this property is actually questionable. Okay. It doesn't look very obvious. Am I right? So if the underlying space X was compact, oh, by the way, there's one thing I can tell. If X was compact, or in other words, if the underlying this matrix space is bounded, then what happens to the Wasserstein space? Let's say bounded means for any xy in x distance x and y less than c is c such that, yeah, i.e. suppose the space is bounded by this bounded metric space. So its diameter, such possible maximum distance is called the diameter. The diameter is finite. So in that case, what should happen to the Wasserstein space? The space of probability measures over the space X with this Wasserstein metric. What should happen? Yeah, it's also bounded. But can you say more? Yeah, and then for all mu nu in Px, so P mu nu is less than or equal to C. Okay, so is it obvious for you? It's just because the distance between any 2 points is less than C. But what is Wasserstein distance? Which is just the mini infimum of possible transfer planes between measures. But what you integrate is just the distance square or power, right? But distance is less than or C. So if you do like this power and then afterwards there's this 1 over P power, look here. this is less than or equal to C and power P, so less than or equal to C to the power P, but then you have this 1 over P power. So anything should be less than or equal to C. So it's obvious, right? So if the space is bounded, then Wasserstein space is also bounded. But now in our case, our space is unbounded. Okay, Rn Rd is unbounded. Okay. But I'm not so Rd is unbounded. So diameter of this Wasserstein space is infinite. It's infinite. But I'm not talking about that. I'm just saying, just pick any two measures. Okay. So any 2 points in this space of priority measures, then there are, I mean, to be a metric space, we want the distance between them to be finite. Okay. But is that obvious? That's what I'm asking. In other words, there's no such mu and nu whose distance, the distance between them is infinite. Is my question clear? Yeah, so, right, so you can spread the measure to infinity. So a priority measure can spread over the whole space. And in particular, for example, there are priority measures such that the variance of it is infinite, right? So you should have learned this in statistics, right? The variance of each priority measure may not be finite in general, okay? But what is the variance? If you consider variance, the variance of mu variance is exactly the same as is integral x square d mu. Yeah, that's a variance. Okay, I minus. Okay, so let's assume mean is 0, then this is true, right? If the mean is 0, then variance is nothing but the integral of the squared x, right? What is this? This is exactly the same as I mean, it's easy exercise. It's the one way to view is this. You have 0 here. You have some distribution SMU. At each point, you consider this distance x squared. So it is like x minus 0 square mu. So that is the same as Wasserstein distance square between Dirac delta is 0 and okay. So here we already see the example that there's a Dirac delta and some measure mu whose distance is infinity. I mean, if mu has infinite variance, but there are such measures mu having infinite variance, okay? And for example, one can cook something like this easily. So this is a priority measure if you compute it, but it has variance infinity. I mean, the same as like this Wasserstein distance from the Dirac at 0 to this measure is infinity. Okay. So that space of priority measures over the whole RD itself with Wasserstein metric itself is not a metric space because the metric can be positive infinity for some measures. So that's why we restrict our measures into those having finite variance. So it's the same as variance of mu is finite. Okay, that is this space P2 RD. Then once you have such restriction, then the corresponding space with Wasserstein metric is a metric space. You satisfy all these required properties for a metric space. At the moment, we didn't say anything about completeness, but this is a complete metric space. Oh, hold on. Is this complete metric space? Yeah, if the underlying space is compact, then P2X is complete metric space. But just in this case, right, so, okay, so the question was, the question from a student, is this a complete metric space? Okay, and then your answer is probably not. Okay, answer probably not. Okay, do I want to consider? Okay, let us just keep thinking about this Wasserstein distance and before answer this question. Okay. Okay. So to understand anything about completeness, we should understand the convergence in the Wasserstein distance, right? Okay. So then here is a theorem. So we have sequence of measures, okay, in this P2RD, and the theorem says the sequence converging to another measure a measure on RD with respect to this Wasserstein distance, okay, as k goes to infinity, is equivalent to, first of all, this is like a weak-star convergence. Weak-star convergence. So mu k has to converge to mu in the weak-star sense, namely for any. So this is continuous functions. C0 should be vanishing infinity. Cx goes to 0 as x goes to infinity. Okay. So for any such continuous functions vanishing infinity, this integral with respect to mu k should converge to the integral with respect to mu. That's weak-star convergence in this case. Okay. But this is not sufficient. We also need this condition that basically the variance of mu k should converge to the variance of mu. This part is variance mu k converges to variance of. Okay. I think Professor Pai already discussed this. Am I right?
Yes.
Okay, so. And then here is an example that why the number one is not sufficient, and then you need number two as well. Okay, so let's not do this, but if you want to check why this condition in particular is necessary, you can just look at this example. Okay. All right, so then, okay, so we now check the understood what convergence means. Okay, then let's come back to this question. Okay, to see whether I can answer this or we can answer that. Is this P2RD a complete metric space? Here, RD is a complete metric space. Then if this holds, then you may even ask that in general, suppose your X is a complete metric space, then would the space of priority measures over X, namely PX, also be a complete metric space? with a Wasserstein metric. So that can be a question, right? Okay, and let's just check this particular case. So what is the definition of complete metric space? We should start with that. Complete metric space means every Cauchy sequence converges. Okay, that is what complete metric space. Okay, so then suppose we have a Cauchy sequence mu k, then the question is, would there be mu such that mu k converges to mu I think I used to know this, but at the moment I don't remember. Okay, so actually,
If I recall correctly, I think it is.
yeah.
Yeah.
So why? Yeah, that's good comment. Okay, so why is it complete? I think one way to do is okay, for Cauchy sequence, this part should, I mean, at least the variance will converge to some number, okay? And of course, you need to construct the limiting measure mu to have the convergence of the Cauchy sequence. And okay, so okay, I don't want to spend more time on this. So probably yes, but it should be your exercise. Okay, one thing I may try to do this is the following. So if maybe hint, if x is separable, that means you have countably many points which is dense in x. Then actually you can do the following. Then dx is also separable. Okay, can use Dirac deltas. So x being separable means we have countably many points which is dense. Then for that countably many points, you can consider the Dirac deltas for each x. Okay, then you have countably many Dirac deltas, and then you can prove that countably many Dirac deltas is dense in dx with W2. And then probably you may be able to use this property and to prove such completeness. But okay, I didn't prepare for it, so I don't want to just say anything wrong. Okay. But okay, at least this is your exercise. All right. Okay, now, so you learned this thing about geodesics. Okay, so in a metric space, a geodesic is just curve in the space. So you have px, and geodesic between mu and nu is just a curve such that if you pick any intermediate points here, let's say sigma t, the distance between these two, this and the distance between these two, if you add them, it's the same as the distance between these two. So that is what geodesic is. That's this basically this what this properties imply. Okay, so that's the geodesic. And then you learned from lecture 6 that such geodesics are given by in the space of priority measures of RD is given by so-called Mechanism displacement interpolation. Okay. Okay. So this is what you learned already. Just to remind you, let us just do a few examples of what this first interpolation is. Okay, this example, if you have delta x0, and if you have 2 points, x1 and x2, and the Dirac delta, half mass here and half mass here, and then the optimal transport between them is nothing but this half of this goes to there, and half of this goes to there. So then the displacement interpolation gives us these two geodesics or two line segments between these points, and then at each t, mu s, for each s, mu s is given by these two Dirac delta points with half mass here and half mass there. Okay. So mu s is half mass of this, let's call this xs, and this, let's call this x2, let's call this x1s, s2s, then x1s, plus half of that x2s. Okay, so that is this example. So the point is, you just find optimal transform mapping with, if you want to generalize it, between points corresponding to your initial distribution mu and the points corresponding to your final distribution mu, and then you have this optimal transport mapping, which gives a matching between points here and then points there. And for each such matching, you draw this line segment, and then you just interpolate these points distributions using these line segments. Then the interpolation will give us some measure in between. That is displacement interpolation. Okay. So for example, there's another simple example in this one. So you have, let's say, a ball, a measure mu, just uniform measure over the ball, and then you have, let's say, measure, let's say, mu1, which is just a Dirac delta. Then the displacement interpolation between them is you just consider the transport, optimal transport between this point and all these points here. Then that will give us just matching between this point and any random points in this distribution. Then you just connect them by line segment, and then you consider let's say the intermediate points when for s between 0 and 1. Okay, then these intermediate points will give you a distribution. That distribution is mu s is the displacement interpolation. Okay, and because we learned Bragner's theorem, given mu and given nu, at each x you have your target is point is given by this optimal transform mapping, the gradient of in this case psi x, right? And then for each x you connect x with this gradient psi x, and then you look at the intermediate points, which is this, okay? 1 minus x s x plus S gradient psi x, that's this point. And then you draw this segment for each x and gradient psi x. So you have many such line segment, okay? And then for each line segment, you have these intermediate points. Then if you correct these intermediate points, you will get a distribution, okay? That distribution is exactly this distribution mu s, this displacement interpolation. So that is Mechan's displacement interpolation. Okay, any questions so far? And the theorem says, the Wasserstein geodesics are exactly given by such displacement interpolation. So the meaning is this: on the spatial measures, you have mu0 and mu1, two measures, and then this displacement interpolation gives us a one-parameter family between these measures, okay, between these measures. So these are measures over X, but they are now points in the space of measures, right? And then such curve gives the geodesic between mu0 and mu1. That is the theorem, okay? Which Professor Parr already presented, right? Okay. So I'm not going to do this. So, okay, so then you want to consider this exercise also. What happens if you consider WP instead of just W2? So here, the theorem is with this distance squared cost. So this theorem is about W2, Wasserstein distance, okay? And the question is, if you consider P power instead for your cost, then the corresponding Wasserstein distance is WP. Then the question is, would we have a similar statement like this Mechan's displacement operation? And if it is, what exactly such a statement is? Okay. That is your exercise. Okay. And all right, so that is your exercise. James, is it okay? Yeah, okay. And then moreover, once you understand, I mean, why this is Mechan's interpolation holds as a geodesic, and then even if you can handle this WP case, you may even ask, what about general metric space X, okay? So this is something you want to think about. Okay. So I mean, there are many other metric spaces than RD, right? So just consider only RD is could be somewhat boring. So you want to consider more general metric spaces, for example, Riemannian manifold. Riemannian manifolds are only a small fraction of examples of metric spaces. There are many other metric spaces, okay? And one thing to help you think about this is that to consider anything like this Mechan's displacement interpolation, okay, you need to be able to draw your two things. For Okay, so you can find optimal transport plan in a metric space. That's good. Okay, you can always do that, right? But one thing you need more than that is this this kind of construction that given x and y, this means you can the line segment between x and y. Okay. But then if so on RD is clear, but if you consider instead x and y in a metric space X, then what should be the, I mean, then it may not be clear whether we can draw such a kind of nice curve, right? So we need, such curves are called geodesics. We need geodesics between each x and y in X. And such a space with geodesics is called a geodesic metric space. Okay, so you can consider then geodesic metric space. In particular, Riemannian manifolds are geodesic metric spaces. Okay, there you can ask the same question, namely, what should be the corresponding statement of Mercant's displacement interpolation, and then its property as a WP geodesic. Okay, am I making sense? James, am I making sense? Okay, good. But these are all optional. I mean, for the moment, you can just focus on RD if you do not like geometry. Okay. But okay, but let me motivate you. I mean, this question, even if you want to focus on RD, still there's a reason why you want to consider this more general aspect. Because from X, you can consider PX, right? X a metric space, you have this another metric space PX. Okay. But then from PX, you can consider the space of product measures over the space of product measures. And you can keep going. Then once you are here, then this is not Rn anymore, right? Then what kind of properties this may have? And on such a space, you will see later is relevant, right? Space of probability measures over probability measures. Okay. Question? I mean, why? I mean, you can easily justify why you want to put such a space. So this X is like each point in X is like an individual person in a society. So X is like society, and PX is a space of groups in the society, right? UBC, SFU, U of Toronto, and Victoria University, and Vancouver. I don't know. There are many like the possible groups in the society, right? Then PPX is the groups of groups. Let's say groups of universities or groups of companies, right? Groups of like activists and so on, right? So this can be meaningful, or you can view this as X is like a cells, each cells, and then PX is like organisms having those cells, and PPX is a group of organisms having cells. Yeah, okay, let's move on. Okay, so we kind of see that such geodesics in the space of probability measures should be something interesting and important. So we want to understand the properties of such geodesics. Okay. So one outstanding question you may ask is that given mu and nu, let's say mu and nu satisfy certain properties. Okay. They are probability measures having some nice properties. For example, they are like smooth. Okay. Then you interpolate them using Mechanism displacement interpolation, family of measures mu s. Then you may ask, okay, what kind of properties mu s may have? Okay. To motivate you, let's consider this question. So suppose mu is a okay. Suppose mu is an empirical measure, namely, it's just collection of Dirac masses. Okay. And nu, let's say, is another collection of Dirac masses. Okay, then what should be? Let's okay, mu is mu zero, sorry, mu zero, and nu is mu one. Okay, then you consider the Mechanism displacement interpolation. Okay, let's say mu s. Then what kind of measure this mu s should be? Same means, yeah, it should be some of them, not this the same points, but there are some points, okay, that generate this measure as a sum of Diracs over these locations, right? It's because displacement interpolation is that you have some kind of optimal transform mapping. So this particle or this Dirac data can be matched to not just one, but maybe the several ones. But still, if you draw this line segments between them, you have only finitely many such line segments at each Dirac data here. So the corresponding displacement interpolation will give you some finite number of points. But if you have like this discrete mass, then you have just discrete set of such points, which will give you that displacement interpolation BS. So this one should be also, let me use the some collection of Dirac deltas. Okay. 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 Now then, let's consider the other extreme case. Suppose mu zero is very nice measure, okay, nice and smooth, and mu one is nice and smooth. Then what should happen to mu s, the displacement interpolation? Okay, so that is some question one may want to consider, right? This is not something irrelevant, am I right? So that is what this theorem partially answers, okay? Okay, suppose you have two measures, let's say mu zero and mu one, okay, and we assume that one of them is absolutely continuous. So it's somehow nice, okay, it's not at least a discrete measure, it's not a singular measure, okay, it's some kind of nice measure, but let's just absolutely continuous. Here we do not assume like smoothness or just absolutely continuous. Okay, and then here mu one is kind of any probability measure. I mean in P, so any member in P2. So it can be a discrete measure or even singular measure. The singular measure is the mass is concentrated in a small dimensional set. That's what singular measure are like, including Dirac masses. Okay. So that's the condition. Then let's just assume that our cost function is just distance square. Okay. Then the claim is when you consider the displacement interpolation, so like some kind of measure in between here, mu s, okay. Then if s is between 0 and 1, not including 1, because I mean, at s equal 1, mu1 can be any arbitrary measure, okay? So no property. But if s is less than or equal to 1, so this mu s can be very close to mu1, okay? Fine. But still not exactly the same. Then you can conclude that this mu s also has this property being absolutely continuous with respect to the Lebesgue measure, induced from the absolute continuity of this initial measure mu0. Okay? So that is a theorem. Okay, question about this theorem? Of course, because mu1, we didn't assume anything on mu1. So mu1 can be anything, in particular, Dirac masses. So example, okay, so example, mu0 is just a uniform measure of the ball, okay? And mu1 is, I don't know, mu1 is like Dirac delta at some point, right? Then mu1 is not absolutely continuous, of course. But if you consider the displacement interpolation, then the displacement interpolation is like you have all these line segment. So your displacement interpolation looks like this. That is mu s. And at least in the picture, it looks like absolutely continuous measure. And that's actually a theorem. Okay. Fine. All right. Okay, this theorem has important corollary. So you can consider not just P2RD, but subset of it, namely the measures are absolutely continuous. So that is called P2AC. So just collect those measures whose variance is finite and that are absolutely continuous with respect to that. And then this space, I mean, I think already Professor Parr indicated that such a space is relevant when you consider, let's say, diffusion phenomena, or later like gradient flow, or I think even Bannerman-Brenier theorem, if you remember, requires some kind of absolute continuity. Okay. And that space is geodesically convex. So here we have Px or PRD. And then we have slightly smaller space, P2RD. P2RD includes all these possibly singular measures, including a bunch of Diracs, okay, or mixtures of Diracs. But then you have much smaller space, P2AC. Okay, and the claim says at each point, mu and nu in P2AC, if you connect them by the geodesic, I mean, possibly the geodesic from mu to nu may go outside and come back. In general, for any arbitrary subset, it's possible. But this subset, P2AC, is a special set, namely, any geodesic between the points inside the subset should also stay inside the subset. Okay, so that is what this line tells. Okay. And having such a property will be important later when you consider, in particular, uh, gradient flows of functionals over the space of measures, because many functionals are only defined on absolutely continuous measures. For example, entropy of measure is only defined for absolutely continuous measures, and so on. Okay. All right. Also, I mean, when we consider Mongian factorifications or Mongian applications, remember, we need density of the measures to even write down the Mongian application. So absolute continuity is something we want to have in many contexts. Okay. And another remark is that such a result is not only on RD, but in a much bigger class of examples, including Riemannian manifold or some other metric spaces, okay? But not any arbitrary metric space, but you need some certain properties of the metric space, slightly generalizing Riemannian manifolds, which is called Alexander space. But anyways, you have some generalization of such a result, okay? But this such generalization is not that trivial, even though the ideas are not that extremely difficult. But you need some work to do that. Even this theorem, this absolute continuity, I would say is the idea is probably clear after you see why it works, but it's not that completely trivial. Okay. Okay. Now maybe we can spend the remaining time to prove such a theorem. Okay. Is that plan good, James? Okay. Okay. So remember that so we are talking about Mechan's displacement interpolation. Okay, so you have measure mu and mu zero, and you have measure mu one, and then you find some optimal transport plans which matches like points x in for mu zero to points y in mu one, and then you have many such like matchings, and then you want to consider these intermediate points and then the corresponding distributions. Okay, so that is what mu s was, and we want to understand what kind of, let's say, regularity, or even in this particular case, whether mu s is absolutely continuous if this mu zero is absolutely continuous. Okay, somehow, I mean, this suggests that we need to understand how these matchings behave. Okay. Right. And let me give you an example. Okay, so the following example belongs to the next slide. So consider, suppose you have some matching between two distributions, okay, like the following. So x goes to y like this, and then this one goes like this. And let's say all these matchings has this corresponding line segment passing through only at this point, okay, at a particular time. Yes. Okay. Then the corresponding mu s if this happens, then the corresponding mu s is what? All the mass here goes to these particular points. So you have concentration of mass at this particular point. So if this was the matching, then the intermediate distribution, the interpolation mu s will be a Dirac mass. Make sense? So somehow, so it's not absolutely continuous, of course not. So to have absolute continuity, these matchings should behave in a certain good way. Am I making sense? So the question. So that is the context of this lemma. So namely, this kind of concentration in the middle will not happen. Okay? So yeah, so the matchings will be like this. No, like this kind of bad crossing behavior. So this quantifies such a thing. Okay. Okay, so this property, I don't think I have time to go into detail. That if you consider xn, x0 and x1 here, and corresponding y0 and y1 here, then you can consider the corresponding y0 s and y1 s there. Okay, and then this estimate says the distance between this y0 and y1 will not be smaller than some combination of the distance between x0 and x1 and the distance between y0 and y1. Okay, so we have this inequality, this directional inequality. So you don't have this like collapsing behavior in the middle. Okay, when when the matching between x and y is monotone. The monotonicity here, I think Professor Parr already explained. Okay, this is a consequence consequence for optimal transfer optimality of the transport planes when the cost function is the distance square. Okay. Okay. I think yes, for the time's sake, let's skip it. I mean, this property you can prove when the transport plane is monotone. Sorry, the other way. When the transport plane is optimal with respect to the distance square thingy. Okay. Then there you have this non-collapsing property in the middle. Okay. I think this was partly covered in Sumik's lecture, so let me skip it. All right. But still, any question about this page? Fine. Okay. Okay, then another thing is this. So that's one ingredient. And another thing is this. So here now, from the points of this intermediate distribution mu s, you consider mapping from here to there, following this kind of line segment. Okay, yeah. So point, let's say xs, and then you go to the corresponding x there. Okay. Okay. And two things. Such a mapping is well defined. So and another thing is that because of this inequality, the distance between them here in this distribution is not smaller than, in a certain sense, the distance between this x and y, x0 and x1. Okay. So from here to there, you may contract, but you may not expand too much. In other words, back from here to there, this distance will not collapse. Okay, so this property is, and if you view from here to there, is translated into Lipschitzness of such a mapping from a point here to there. Okay. So we will define a mapping. Let's say GS. Okay. In such a way that you have mu0 and mu1, and then in between you have mu s, and you have some intermediate point xs, and that corresponds to x0 and y. Let's call this x1, okay? Then you consider from this s to x0, this mapping. So if you have another point here, that point will correspond to another x0 prime and x1 prime. Okay, then you consider this mapping. So you send this xs to x. That is your mapping GS. Then the previous inequality over here correspond to that. Such a mapping from here to there is ellipsis. Okay. And it transports the measure mu s to the measure mu 0, because it's just by definition of this construction. Okay. Yeah, so this line exactly is the same as what I said. So you have this SS, in this case is Z, interpolating these 2 points, in this case X and Y. Okay, then you send this point into this one end. Okay. And several things, such a mapping is well defined, that for this, no 2 points coming to the same points. So there's no such crossing, which is a property of having this this inequality. So no 2 points goes to the same points in the middle. Okay. And this GS, okay. And because of that inequality again, this distance is not smaller than, in a certain sense, the distance between the corresponding points for mu 0. So that is this ellipsis property. And the mass here is transport to mass there to mu 0. Okay. Okay. Any question about this lemma? So basically, we have what he say is we have a ellipsis mapping from this intermediate mu s to mu 0. Okay. Of course, you can do the same game from mu s to mu 1 too. The mapping here is also ellipsis if as long as s is less than or equal to 1. Okay. Now, if s is 1, the ellipsis constant will blow up. Okay. Anyways, but we are interested in the mapping from mu s to mu 0. Okay, and that's the situation. This is the last slide. Okay, what is good when we have a ellipsis mapping? Okay, in terms of regularity of a measure, or in terms of measure. Okay, what is it? Let's just consider for a moment the so-called Hausdorff measure. Okay, Hausdorff measure is a representation of Lebesgue measure. Okay, so there's a theorem that Lebesgue measure is the Hausdorff measure times some constant. Okay, so what is Hausdorff measure? What is such a representation of Lebesgue measure? Is this: you have a set, some set, let's say S, and then you cover the set by some other sets like poles of some finite diameter. some given diameter, let's say less than or equal to S, okay? You cover that. And then you look at the sum of the volumes of such balls, okay? So basically, then the volume of such, sum of the volumes of such balls should be bigger than or equal to whatever the set it covers, okay? And then you take infimum of such covering. And then now you refine the scale of how small the balls should be. So you may use like a bigger scale, but to cover S, but then you restrict the covering to smaller and smaller scale, so that you have more and more refined covering. Okay, and then such a limit is the Hausdorff measure. Okay, so I don't have time to spend a lot on this, but this is something very useful to learn. So I don't remember any. I mean, just I think you can just check Wikipedia to learn more about this Hausdorff measure. Okay, check Wikipedia. This is something useful to learn. Okay, so then the point is that Hausdorff measure gives a representation of Riemann measure. Okay, and then then what is the property of Lipschitz mapping regarding Hausdorff measure, or equivalently regarding the Riemann measure? Okay, is this: if you have a mapping T from S to TS, then this S is like a set like this, and TS is a set like that. Then the Hausdorff measure of this image is less than or equal to the Hausdorff measure of the source set times the Lipschitz distance, so Lipschitz constant of the mapping to the power the dimension. Okay, so this is, sorry for giving it also as an exercise. This is an exercise. Okay. One starting point is that if you look at just the diameter, because Lipschitz is about the distance structure. So first, you want to consider how this diameter changes on the Lipschitz map. But this is obvious that the diameter of the set in the target is bounded by the diameter of the original set times the Lipschitz constant. But then if you look at the definition of Hausdorff measure, you have just diameters to the power D and summation. So if you play with this, you can get such inequality. But this is for Hausdorff measure, but the important thing is that Hausdorff measure is equivalent to Riemann measure. Okay, then once you have that, okay, now maybe I can spend 5 more minutes. You can prove this absolute continuity of the interpolation mu S when mu 0 is Riemann measure. How? The proof now is very easy. So let's say you have mu 0, which is absolutely continuous. Okay, and mu 1 can be any like singular measure. Okay, doesn't matter. And then you have in between you have some kind of mu S, right? Okay, now what is absolute continuity by definition? Okay, I didn't say what absolute continuity means. Okay, absolute continuity, practically speaking, it means the measure has a density function. Okay, but then it is a result of I think what is the corresponding theorem for that? What?
Radon-Nikodym.
Radon-Nikodym, right? Radon-Nikodym theorem. But that definition is equivalent to saying that continuous is equivalent to saying that for any S, a set, measurable set mu S being 0 implies the other way. Okay, the other way. Mu S. Okay, let me use E. this set of S, for any measurable set E, mu S E is 0 if E has 0 real measure. Okay, so that is a statement equivalent to being absolutely continuous. So we will prove this. Okay, so we pick any any uh, any set, any measurable set E, okay, which has 0 mass, okay, and we want to prove that mu S E is 0. Okay, how? We send this set by the mapping GS, then you have the corresponding image GSE. Okay. What do you know? Maybe let me use the bottom shell, bottom space. What do you know? We know that because of the previous lemma, I mean, we know GS is ellipsis. Okay, ellipsis GS is less than 1/1 minus S. Okay, but here our S is less than less than 1. So this ellipsis constant is finite. So the volume of household measure of GSE is up to some constant multiple less than or equal to the household measure of E. Right? All right. Fine. But we already assumed that this is 0, right? So this has to be 0. Okay. Maybe. Okay. So GS, this one has 0 measure. Okay. Then why does it imply that mu S E is 0? But remember, this map pushes forward mu S to mu 0. Okay. That's by construction. So we bring this mass to the measure the mass mu 0. Okay, then what happens? Then mu 0 of E, sorry, mu S of E, what is it? Or maybe to be more transparent, we can do the following. Mu 0 GSE, okay? We have this pushy forward thingy, okay? That means it is the same as mu S GS inverse GSE. So by definition of pushy forward. So remember, T pushy forward mu to nu is the same as for all E, nu E is the same as mu T inverse E. Okay? We are just doing that. And now, so this G inverse GS is small, I think bigger than or equal to, yes. Yeah, so this set contains E, obviously. So we have this inequality, okay? Right? So we have this thing. Now, mu 0 is absolutely continuous with the back. So GS house of measure, which is the constant of Lubeck, that is 0. And now that implies mu 0 G S E has to be 0. Therefore, in conclusion, this has to be 0. So this has to be 0. So that is the end of the proof. So we start with measure 0 set E, remember measure 0 set E, and then we ended up saying mu s E is 0. Okay, sorry for overtime again. Okay, let's stop now.